Hello, my name is Cole Francis, and today I'm going to talk about the procedure that we did for Lab 2 and the results that we got from the model used in Lab 2. So the overall purpose of this lab was to prepare charged pieces of Scotch tape by quickly removing two pieces apart, to observe how the two pieces of tape interacted with each other, and to determine approximately how much excess charge was on a piece of the charge-clear tape. The difference between this lab and Lab 1 is that in this lab, we are treating the tape like a string of point charges instead of a single point charge. Next, I'm just going to go through some of the Lab 1 calculations that we had to do, which also apply to this lab. So the materials we used for this lab were a roll of clear Scotch tape, a meter stick, a flat surface to charge the tapes, and two whiteboard erasers to support the tape that we used later to be the floating tape. So as far as the relevant physics principles for this lab go, there are three main ones that we considered. The first was Coulomb's law, which provides a model to calculate the electric force from one object acting on another. There's also Newton's first law, which is that the net force acting on an object at equilibrium is zero, which is important to the floating tape, which we then use to determine the charge on the tape. And also Newton's second law, which essentially states that an object's acceleration is based on the net force acting on it and the object's mass. So some key observations that I made in lab was that the charged tape was attracted to neutral objects, which means that it had a positive or negative charge, as either would be attracted to neutral objects due to the polarization of the neutral object. Also, the charged tapes repelled each other, which meant that they had the same charge. Charged tapes also were repelled by a negatively charged pen. This indicated that the charged tapes were negatively charged, as like charges repel, and we knew that the pen was negatively charged. Also, the floating tape was not moving while it was floating, which is important because that indicated that that piece of tape was at equilibrium, which meant the net force acting on the tape equaled zero. So as far as the key measurements were made in the lab, were the length of the tape, which was 0.17 meters, the mass of a single piece of tape, which was determined using the length of the tape and the density, and that came out to be 0.0000017 kilograms. The distance between the two tapes at equilibrium, which was 0.05 meters, and then also the calculated magnitude of the gravitational force, which is 1.6677 times 10 to the negative 3 newtons, and therefore the magnitude of the electric force, which had to be the same since the tape was at equilibrium, and that was also 1.6677 times 10 to the negative 3 newtons. So the key calculations that I made for this lab were that the charge on tape B ended up being 2.15232 times 10 to the negative 8 coulombs, which makes sense as it's a pretty small amount of charge. The number of excess electrons on the charged tape ended up being about 1.3 times 10 to the 11th electrons. The number of atoms on the sticky part of the tape was 3.4 times 10 to the 17th atoms, and the ratio of the excess electrons to the atoms was about 4 times 10 to the negative 7th. And this is all, I'm going to show how I calculated all these on the next slide, but the most important calculation here was the charge on tape B, which is the purpose of the lab, and that was determined using Newton's first law at equilibrium. So, as you can see here from the free body diagram, since the charged tape was at equilibrium, the force of gravity acting downwards on the tape equaled the electric force from the tape on the bottom acting upwards on the floating piece of tape. Therefore, by setting these two forces equal to each other and being able to easily calculate the gravitational force, I was able to create an equation to solve for the charge on the tape by using Coulomb's law for the electric force, and then plugging in all the values and moving the charge quantity to one side of the equation and all the values to the other. This is shown in my calculations here, and you can see that that got me to my 2.15232 times 10 to the negative 8 coulombs. I then was easily able to set up ratios to the charge of an electron to find how many excess electrons were on the tape, and to find how many atoms are on the tape and to find that ratio of electrons to atoms. So as far as the computational model goes for lab 2, you can see here that you can see a lot of the code here, and basically what it does is it assumes that the tape is a string of 100 point charges, and it finds the electric field from each of those point charges and how they act on each other. And I first used the charge from lab 1 to assume the charge of the tape, but as you can see in the picture, the electric force was less than the gravitational force, which is not what it actually is in real life, because the electric force and gravitational force must cancel for the tape to be in equilibrium. Because the electric force needed to be increased, I then played around with using different charge values, and I came to the conclusion that this charge value ended up with an electric force that was very, very, very close to the gravitational force, which is a lot more accurate. And it is accurate that the system is now in equilibrium. This is probably because a lot of the charges, electric forces cancel out with each other, or electric fields, sorry, cancel out with each other due to the superposition principle for electric fields. So it leads to the total charge of the tape being much greater to achieve the same force as if the tape was just a point charge. In conclusion, the estimated electric force in the previous lab was less than the estimated electric force in this lab, and this is likely because the model in this lab is a lot more realistic to how tape behaves and how the electric field from the charges that make up the tape likely interfere with each other due to the superposition principle for electric fields, and therefore would take an overall greater charge on the tape to achieve the same amount of electric force from the bottom tape on the top tape. Thank you for watching.